So in this video, I wanted to go over all the different scenarios that you could see with Le principle and see how reactions would react if this equilibrium reaction was put under stress in a certain way. All right. So for these scenarios, I'm going to just use a very simple reversible reaction right here. A going to B. All right. So we could write this expression right here. Concentration of B raised to the lowercase b, which is the coefficient there, over top of A raised to the A. All right. So one way that I think it kind of helps to envision what happens with an equilibrium reaction is to think about, like, let's think about a seesaw. All right. And think of equilibrium as the position that this seesaw likes to be in. All right. So let's say you have a little, at equilibrium, there's a little bit more of this black stuff and a little bit less of this red stuff. And the equilibrium is however much of these things is required to keep it at this position right here. All right, so keep in mind that could mean, a small pile of black with, a smaller pile of red, but you still have more black than red. Or you could have a really big pile of black and a bigger pile of red, but you still have more black to red. So the equilibrium is that ratio between the amounts of these things here. So for this particular equilibrium, we're just going to pretend that there wants to be more of the black stuff than the red stuff. All right, and in our reaction, the black stuff can get converted to the red stuff, and the red stuff can get converted to the black stuff. It's a reversible reaction. All right, so and all the time, you have some of the black becoming some of the red, and some of the red becoming some of the black. But as long as those rates are balanced, like once this thing's at equilibrium, if this black thing became a red thing and one of the red things became a black thing, well, it doesn't change the amounts of these. All right, as long as for every one of these that goes this way, one of these comes back over here, things stay balanced. All right, so let's think about what would happen if we were to change the equilibrium, excuse me, by either adding things or taking things away. So let's pretend that this thing is at equilibrium and we add reactants. All right, so if we add some of this stuff on the left, all right, well, let's think about what would happen. All right, if you added some stuff over here, that's going to make this thing tilt downward on this side. All right, so how do we move things around to get back to this equilibrium position? All right, well, if we add some stuff over here, the way that we're going to get back to equilibrium is by turning some of this stuff in over here, temporarily turning some of this stuff over here into this stuff over here. So what we're going to do is we're going to temporarily, so we're going to have the forward reaction temporarily speed up. So this one going from black to red temporarily speeds up. All right, what would that do? All right, well, when some of these get turned into some of these, all right, or when that's happening faster than the reverse process, you're going to reduce the amount that you have over here. You're going to increase the amount that you have over here, and you're eventually going to get back to that equilibrium position. All right. So when that happens, that's called shifting. We'll say that the reaction has shifted to the right, all right, which means that the right reaction is temporarily going to be faster than the left reaction, all right? So what would happen if products are added, all right? So what would happen to this if we added some of the red material onto this, all right? Well, that would temporarily make this side right here too high for the equilibrium. So how do we get back to equilibrium? Well, some of these reds have got to be turned into some of the blacks. All right, so the reverse reaction is temporarily going to speed up. That reduces the amount of the product. All right, so we're going to reduce the amount of the product and increase the amount of this over here, and that would restore that equilibrium. All right. What if reactants are removed? All right, so what if this were to be at equilibrium and we took away some of these black things? All right, so not reacting them to make red things, but we just took them away. All right, well, that's going to mean that if you can envision this, this thing's going to level out a little bit more if we remove some of the stuff from over here. So how do we get it back to this equilibrium position? All right, well, what's going to happen if you do that is that we can, well, what we need to have happen is some of these red things need to be turned into some of these black things. All right, so what's going to happen is that the forward reaction, this forward reaction is going to actually slow down a little bit. So instead of the reverse reaction speeding up, think of it as the forward reaction slows down. So remember, at equilibrium, it's not like, remember, you still have the forward and reverse reaction going on. So if you slow down one of them, but the reverse reaction keeps going at its normal speed, it's essentially going to turn some of this stuff over here into this over here. So if we slow down the forward reaction, if we slow down the right reaction, but the left reaction keeps on going at its normal pace, you're going to that's going to increase the amount of A over here, reducing the amount of this over here. And that's when you do that, that's considered shifting left, right? So shifting right is anything that increases the amount of the products. Shifting left is anything that increases the amount of the reactants, all right? And the last scenario would be, what if we removed things over here? If we remove things over here, you can see it's going to be tipped a little bit more towards the left. How do we get it back to equilibrium? That would temporarily slow down the reverse reaction, all right? And if the forward reaction keeps on going at its normal pace, that's going to turn some of these guys into the red, and we're eventually going to get back to that equilibrium, all right? So as an example, let's pretend that we've got this reaction right here and that it's at equilibrium, all right? How would this reaction respond if NH3 was removed from the reaction, all right? So again, what that would involve is we are going to be removing a product from the reaction, all right? So let's look at our scenarios here. If a product is removed, what's going to happen is that means that the reverse reaction is temporarily going to slow down while the forward reaction keeps on doing what it normally does. And that's going to, that means that the right arrow is going to be larger than the left arrow. Therefore, it's going to be considered a shift right. And what that's going to do is that's going to increase it's going to temporarily increase the amount of NH3 while decreasing nitrogen and hydrogen. And it's going to do that just temporarily, all right? Just until you get back to that equilibrium position, and then the forward reaction is going to equal the reverse reaction, and then that equilibrium will stay where it's at.